students, I would like to lead us through a discussion of the dependence of free energy on pressure, specifically really emphasizing the relationship of Gibbs free energy to equilibrium. I want to stress this sentence that I have in caps. A system at constant temperature and pressure will always proceed spontaneously in the direction that lowers its free energy. That is something we need to keep in mind as we're talking through this note packet. Now, as a reaction proceeds, we know that the concentration of our reactants and products are changing, and that can have an influence on pressure changes if we have gases as reactants and products. Now, what role does pressure play on Gibbs free energy? Remember, Gibbs free energy is delta H minus T delta S. Well, as pressure changes, does that change enthalpy? No. That has no relationship on exothermicity or endothermicity. But what about disorder? Well, if we have reactants and products as gases, we know that pressure and volume are integrally related, and volume can help with randomness. The greater the volume, the more opportunities for different positions. So entropy in a bigger volume is greater than in a smaller volume. So we can make the connection that entropy at a low pressure is greater than entropy at a higher pressure. Specifically, and your textbook does go through how this is mathematically derived, if we want to freeze our reaction at one point, the Gibbs free energy at that point is equal to standard Gibbs free energy for your products minus reactants plus RT natural log of your pressure. Now R, because we're dealing with energy, we want to use the 8.314 joule per Kelvin mole. Temperature, of course, being in Kelvin. However, we know that for a reaction, we want to look at the change in Gibbs free energy. So here's where we get this reaction. If we're dealing with pressures, then we know we want to deal with our equilibrium expression. But here, we don't know if we're at equilibrium or not. And so it'd be more proper if we call it Q. And so that would be, of course, the pressures of our products over the pressures of our reactants. If you want to take a look here, I have an example with the Haber-Bourne process of now, if we're at equilibrium, it's K sub P, but we would not assume that. So we're going to call it Q sub P. So I've just changed, instead of just the pressure of my system, now I want to look at the relationship dealt with through Q sub P. So we have this equation where the change in Gibbs free energy is equal to the delta G naught plus RT ln Q sub P. And I have an example here where we will have to apply this equation. Now, you're given the reaction, you are given the temperature, and you're given the pressure of your gases. Notice my product is a liquid. So I just need to know the pressure of these guys because my K would only be due to the concentration of my reactants or the pressure of my reactants. Okay, now if I'm looking here, I'm not given delta G naught for the reaction. So what I had to do was to find the delta G naughts of formation of my products and my reactants, interpreting it per the balance equation, and I had to calculate it. And being careful of your signs. Okay, so that will be this. R 8.314, T converting 25 to Kelvin. Now, I'm going to input my pressures, not assuming at all that I'm at equilibrium. So calling this Q sub P, do you see my numerator is 1, plugging in my pressures, then I end up with this as my value for delta G. Okay, now, what is the value of this? Well, the value of this tells me that where I am in my reaction, at this temperature and these pressures, I'm going to compare that to what delta G is, delta G naught. Okay, my delta G is the real world, this is my reaction situation. This is a theoretical product minus reactant target. At this, okay, I'm negative 38 kilojoules per mole. Here, I'm only negative 29. So this is actually a quote-unquote more spontaneous situation. And if we think of Le Chatelier's principle, I have pressures greater, and so that should encourage the production of product. So it's more spontaneous in the direction it's written at these conditions. So that is the value. The delta G is actually telling me and relating me to equilibrium, but it is giving me a value that I can use to judge the spontaneity of my reaction. All right. Taking a look at this. Here's a great website that, definitely says we have to keep in mind, why do we go to equilibrium? Equilibrium is favored kinetically because it's the lowest energy situation. However, thermodynamically, also the lowest energy as far as free energy is concerned. Or the most energy has been released that can be used for work, as our discussion of free energy talked about. Now, we need to make sure that we understand the difference between G and G naught. So if you want to take a moment and pause and read through this. But I think this makes most sense also if we take a look at this graph. I'm going to talk us through this, but if you want to pause to read this, it's a really phenomenal explanation. Okay, if we look at this reaction. Now, the delta G naught is the Gibbs free energy of my products subtracting the Gibbs free energy of my reactants. And here, it's an up-here bottle. It's positive 5.3 is my delta G naught. Now that again is a theoretical, never realized situation because I'm comparing the delta G for my product minus my reactant, not necessarily the go-between of the reaction. Where the delta G, whenever I use this equation, the delta G is really telling me, as I am proceeding through my reaction, what is the real free energy? And equilibrium will occur in this valley at my position of lowest free energy. Just like that picture of that little gal on a bike, we know she's naturally going to head toward the lowest point. Naturally going to lead to the lowest point. So my situation in equilibrium will, in this case, favor more reactant, won't it? Favor more reactant because here's my valley. If I'm looking at my ratio of moles of reactant and product, here's where my equilibrium position will favor. All right, so back to the reaction sheet. And talking about the note packet, the same idea of rolling downhill. If we look at delta G naught, it's just looking at where do you end and where do you begin. But delta G actually allows us to see that, there's actually a lower position that's a combination of reactant and product. This is actually the lowest energy, and that's where, and why equilibrium exists for this specific reaction. Okay. I really like this contrast. From the beginning of our equilibrium unit, talked about why does equilibrium exist? Well, equilibrium exists according to a kinetic chemist when forward rate equals reverse rate. But to the thermodynamic chemist, equilibrium occurs when you're at your lowest point of free energy.